Welcome all. So in the previous lecture we discussed about physical interpretation of a gradient. So we defined about a particular function, or particular scalar function about a particular point P. Then we moved to about a point Q, where we defined about the change of that particular function d phi, right, along the direction dr. So dr is a position difference or distance between point P and Q with a function that is phi, scalar function phi, right. Then we move to the particular point P to Q by the variation of that function with respect to x, y, z respectively. Then we defined about the gradient of that particular function with operator del phi, right? So in this lecture we are going to discuss about physical, that is nothing but divergence of a vector function. Divergence of a vector function, right? So now, as we know that what exactly the mean by vector, that is nothing but a vector function. So we already know about the vector function is nothing but a that is vector is nothing but it's a physical quantity. It is physical quantity which has both magnitude and direction, magnitude and direction, right? So direction is called as, that physical quantity is called as a vector quantity or vector function. A function of that it is a function of let if I define a vector function, that is if I define a vector function a vector, if it should be a vector or a physical quantity, it depends on a position, that is in the position coordinate of a particular point. If I define a vector A at a point P in a particular Cartesian coordinate system, if I consider this one as a x and y, then if I consider this point P here, if it should be a vector, it should have that quantity should have magnitude and direction along that particular system where it is lying. Means that a vector is a function of positions, that is x, y, z in Cartesian coordinate system. As we have defined the same scalar function in the same way, that scalar function phi we defined as it's a function of x, y, z. Means it is also a physical quantity. Both scalar and vectors both are physical quantities which depends on space coordinates. That is, space coordinates means x, y, z are space coordinates. Here the main difference between this phi and a vector is it depends, this vector A depends on direction, but this phi depends on it has only a magnitude but not about a direction. So it has both magnitude and direction, that is vector A. That's why we define this one as a vector, the function which depends on space coordinates and which has magnitude and direction along those particular space coordinates, then that is called as a vector, right? So here I will define as I defined this vector A is a function of position coordinates x, y, z. Its dependency will be on all three coordinate systems. So here I'll define this a vector. It depends on all three coordinates. If I define its magnitude along x-axis is ax and its direction will be along x direction, that is I cap. Then here ay be the component of that a vector along y direction, then az be the component of that vector along z direction. Here ijk's will represent what I represent about x direction, j represent what y direction, k represent what z direction, right? So these ax, ay and az, all these three are the vector components. These are vector components. Means those are the parts of the vector A along all different directions. Means with respect to x direction, ax is the component of A, and along y direction, ay is the component, and along z direction, az is the component of the vector A. Right. So here the divergence of a vector quantity or vector function is defined as, so yes, in the previous class, as we know about the operator del, that is del operator, it is about, it's a differential operator, right? So you know that this del operator is a differential operator. Differential operator in a vector form. In vector form, that we defined as a del vector del as a del is equal to, that is dou by dou x of I cap plus dou by dou I of j cap plus dou by dou z of k cap. Right. See, if you look at this, this is del is a differential operator, but it's in a vector form because I, j, k's are there. It has magnitude and directions. So that's why I will define this del vector as a differential operator as a vector. Differential operator as a vector. Now del vector. Then as I have taken the vector function, that is a, if you take the dot product of these two, or if you take the vector product of these del operator and a vector, it will become about a divergence. That means this divergence of a vector is nothing but it's a dot product, or it is a vector product of a differential operator vector and a vector. So a is the quantity function, and here del is the operator which is acting on that vector a. In case of gradient, we define this del will act only on a scalar function, that is a scalar product. It was about a scalar product, means it is only just in a normal differentiation type. But when it comes to the divergence, it is nothing but it's a vector differentiation, vector operator product with vector a. So it is a differential operator which is a vector. There is a dot product between a vector and the differential operator, then that is called as a divergence. Hence here divergence is defined as, divergence is nothing but it's a dot product of a differential operator and that vector is called as divergence of that particular vector. Here if I take the dot product, as I have defined about divergence, if I take the dot product of these two, or a vector product of these two, that is del operator, it's also vector dot a vector. Now as I have defined both a vector and del operator, here is a vector and here is a del operator. Now if I take dot product of these two, I will get as, that is first if I define about del operator, that is dou by dou x of I cap plus dou by dou I of j cap plus dou by dou z of k cap dot a vector, as I have defined above, that is ax I cap plus ay j cap plus az k cap. Right. So these, if you take the dot product of these two, as you know that that is I dot I is nothing but I dot I unit vectors dot product is equal to 1, that is j dot j is equal to 1, then k dot k is equal to 1. But if you take the cross dot product of different coordinates, that is I dot j, that becomes 0. So you know about all these things from vector calculus, that is j dot k is 0, then k dot I is 0, because this dot product of perpendicular axis is always 0, then dot product of the same axis will be always equal to 1. So if you do the mathematical calculation of these products, vector products, then we get, that is dou by dou x of ax component, only the x component will survive here, then dou by dou I of that is ay component, then plus dou by dou z of z component, that is az. So this is what the total dot product of del vector and then vector a. So this is given by the divergence. Divergence is nothing but it's a dot product of a differential operator and a vector function. Right. Now if you look at this particular equation, as del is nothing but it's a vector, del operator is nothing but a vector or differential operator, and here E is also a vector. Now if you look at this total resultant of these two, it is a scalar quantity. It is a scalar quantity because it is only a magnitude of differentiation, but not about the directions. means the divergence of a vector is always a scalar one. So divergence of a vector is always a scalar one, scalar function. So in case of divergence, we defined gradient. We defined the gradient of a scalar function was a vector there. Here divergence of a vector is a scalar quantity. Here we are not getting any direction dependency of those quantities. Only that is change of that particular function with respect to x we can get here, but not about the direction. Here it is only change of that function along x, change of a function along y. This is a change of a function along z direction. So this is what exactly the mean by divergence. Now, what exactly the physical significance of this divergence of a vector? So physical significance of divergence of vector is given by. So divergence of a vector is the divergence of a vector is given by, it is the limiting value of, it is the limiting value of net outward flow of a some physical quantity physical quantity like a fluid or electric flux through the surface per unit value per unit volume per unit volume, right? So here you can see the definition of this divergence is, it is about the limiting value of a net outward flow of a some physical quantity like fluid or electric flux through a particular surface in a per unit value. So here it is. Now I will define particular here. I'll define one area. Here is the particular surface volume. I'll consider this is the total volume V, and here if you take any particular physical quantity, so I will define this is the total volume V, and the surface area of this one be a capital S. So let the surface area be surface area of this one, of this area, that is be capital S, right? So here S is the area and V is the volume. Let a particular vector, let a vector A is coming out of this particular area. So if I define the particular function A, it is coming from this surface. So if I define a particular point P here, a particular point P on this particular surface, and I'll define a vector which is coming from inside of this area through this particular point P here. So I'll define a particular point P on this area with a value V, right? So as this vector A is coming, if it comes out of this surface, then we call this one as a outward flow. If it comes out of this one, it is called as outward flow. Means that vector is coming out of this particular area on this volume containing the surface. Yes, right. So this is a small area, that is P point, that vector A is coming out of this one. If any physical quantity which comes out of the volume, that is called as a outward flow. Means let if this A defines about it represents about the volume of the liquid or any physical quantity flowing out per second. That is maybe I can define this one as a volume of that particular physical quantity, volume of a physical quantity, it may be anything, vector A, physical quantity coming out per second per unit volume. Generally, we define this one as a rate flow, right, or flow rate. In case of liquids, we define this one as a flow rate, which is coming out of the particular area. So if I define any pipe here, so if water is coming out of this one, the outward flow of this liquid through this particular surface S, or a particular volume, if I take volume, that is a rate flow we define, right, or flow rate we can define. So that is the volume coming out of the particular area per second, in particular that with respect to that opening or any system. So this is a system with a volume V, and that physical quantity which is coming out of that one per unit time. So that is called as a physical flow rate we define in case of liquids. So similarly here also, as I have defined the area, that is S here, that is a point P, vector A is coming out of this one, means that is the rate of a flow of a physical quantity which is coming out of that one. So if anything, any physical quantity which comes out of a particular volume per second through a closed surface of that surrounding, because here I have taken this one as this volume is a closed one. This is a closed surface with having a volume, and that physical quantity which is coming out of this total volume per second is defined as a rate flow. If it comes out of this one, we define that is nothing but a divergence. As I have defined, the divergence is nothing but it's a net outward flow of a physical quantity, right? So if this physical quantity is coming out of that one, we define the divergence of a vector is a negative one. So if you take that is if that physical quantity coming out means that divergence, that is divergence dv of that vector is always a negative quantity, right? So means this divergence of vector A at a particular point is negative, means that is coming out of that one, Then if the liquid flows into the particular point in the defined volume, then we take the divergence as a positive, because with the same volume of V through the surface area S, if that vector flows inward to this one, then we define this one as a divergence as a positive one. Hence overall what I am going to define is if through a particular surface, if any physical quantity comes out, then we define this one as a divergence. It is a net outward flow or net inward flow. If it is net outward flow through this particular surface per unit time, then we define that one as a rate flow. If that rate flow is outward, we define that divergence as a negative. It will be a negative one. Then if it is inward, then we define this divergence as a positive one. So it depends on the direction of those physical quantity which is coming out or inward. But overall physical meaning of this divergence is nothing but it's a net outward or inward flow of a particular physical quantity coming out of a defined volume and defined surface area of that closed quantity or closed surrounding. So that is called as a divergence, right? So here another one main important concept of this one is, if I consider the volume V of that particular surface, so I will define a particular surface here, right? So this is a surface having volume V, and I will define a point P here. After this, on this surface, I will define a particular point P, right? Now let the vector quantity A that is at a this point P, I will define this one as A vector, right? I will define this one as A vector. Now the normal to this surface we always define outward perpendicular to the tangent of that one or surface of that one. I will define this one as a normal n cap, right? Now if this A vector A makes an angle theta with this normal, then I will define this area around this particular point, I will define this one as a ds. This is a small area, right? Now this vector A is coming out of this small ds area per unit time through that surface. Now the small area surrounding that particular point P and the direction of the flow of this vector A be the outward flow. So I will consider this one as a outward flow. This one is outward flow, right? Outward flow. Now, according to the concepts we have discussed or we have studied in case of electric field, that the total quantity which is coming out of the particular surface area is called as a flux, right? That is flux. Flux means a particular quantity or a vector A which is coming out of a surface, is called as a flux. Here physically we define the flux is nothing but the quantity or a vector coming out of that surface in that direction of the normal to that surface. So here dot product means that physical quantity is in the direction of a surface only. Hence here I will define that flux is equal to, because this vector makes an angle theta with the normal, means that a vector component of A along this normal is called as A cos theta, or it can be defined as A cos theta, because the normal in this direction and the vector is in this direction, the flux will be always defined along the normal of that surface. It means if this is a A vector, means this component is A cos theta. Now if you take the dot product of this ds small area and the vector that is defined as a flux, means that a physical quantity which is coming out of the particular defined area, that is ds, then that is called as flux, and it should be in the direction of normal to that surface only. That's why we define the flux as A cos theta ds. Hence this is nothing but a flux that I define as a dot ds. Right? Now if I take this, if this theta is 0, if this theta is 0, we define that flux as A ds only, right? A ds. Now the total flux of that particular physical quantity out of the whole surface is defined as, now it is just only small flux, means this is small quantity. If you want to define the total flux is defined as total flux of that particular field out of the whole surface. Now I have defined only ds area. Here I have defined only a small area. If I calculate the total flux of that physical quantity through the full surface area, that is capital S, then we get by integration, that is total flux is equal to that is surface integral of A vector that is ds vector, because it is an area element. Here this ds is nothing but a area element. Here A is a vector, and this surface integral, double integration, is called as surface integral to calculate the total area of that surface. Now if you look at this diagram, here I have defined the ds small area. If I integrate this total area into that, it becomes, that is capital S. But as I have defined this one is a spherical area, if this volume is very small, if this total surface, this round surface, if it shrinks to a small area, if this V volume of this one is very small, very small, now this physical quantity, it looks like, for this, if volume is very small, now this physical quantity, that A vector, will look like it is coming out of a particular point. Now I will shrink this total volume into a very small volume, about one single point. Then now that physical quantity coming out of that point is defined as a divergence. Means through this particular single point, that a vector is coming outward, right? Here, wherein for full area we define that area is coming out of this one. If you take the volume is very small, then this volume will shrink to a particular point. Now then the outward flux per unit volume will be defined as, that is outward flux coming out of volume V, that is very small volume V, that is outward flux per unit volume. Outward flux per unit volume, that is nothing but flux. We know already. Flux. We know flux per unit volume. Unit volume can be defined as, that is flux. We already know that is nothing but a surface integral of a vector dot ds. This is a flux per unit volume. If I define this one as a volume V. Now, as I have taken that volume is going to very small, means I will define that delta V is tending to 0. Means if I apply the limit here, limit delta V is going to 0, means because I am shrinking volume to dV. Volume is getting very small. Means that whole volume seems to be like a point. Out of that point, a vector A is coming out, right? Here, if I define the limit, if I apply the limit here, limit 1 by V of a surface integral of A dot ds. Now, this quantity will represent about a divergence. It represents about the divergence. Means the divergence of a vector is nothing but it is a limit of delta V tending to 0 with 1 by V surface integral over A dot ds. Means if any quantity which is coming out of a defined volume with a closed surface, then that is nothing but a flux. If that volume is going to be a small volume, that is dV, or if it is shrinking to the particular point P, so if any quantity coming out of this point now is defined as a divergence. Means the physical meaning of the total divergence is nothing but it is everything is about outward flux or inward flux only. But when it comes to the single point, if anything comes out of a single point, then it is called as a divergence. As we can define the same point in case of optics also. If in case of concave lenses, in case of concave lenses, yeah, all lights which are refracted by, or light beams which are refracted by this concave lens is now taken to be a diverging lens, because all lines will looks like a diverging from a single point. They are coming out of a single point. So now as we defined this point as a diverging point, similarly here, if in a case of a physical or physics quantities, if any quantity which is coming out of a single point now is defined as a diverging quantity or divergence of that physical quantity. For example, if you take about electric field, for example, for electric fields, we define the divergence of an electric field del dot E, we define always as a limit, that is delta V tending to 0, that is 1 by V surface integral over E dot ds. Because E dot ds is nothing but a flux. We already know electric flux. This is called as a electric flux. Now the same electric flux, if in an electric field it is coming out of a single point, then we define that one as a divergence. So it is nothing but once again we can link between integral forms and differential forms using these divergence and gradient operators. But main thing about the divergence is it's about a physical quantity which is coming out of a particular surface over a unit value, that is called as a divergence of that vector quantity. Similarly, we are going to use the same physical interpretation of this divergence in case of Maxwell equations that we are going to discuss in the next class. But the main concept of this divergence is it is like a vector quantity which is coming out of any surface or any closed volume can be defined mathematically by using this divergence or del operator. It is nothing but it is direction dependent. Totally that vector which is coming out of that volume, it is directional dependent. That's why we are going to take a dot product of or a vector product of this a differential operator and a vector quantity A. So this is what overall theme about divergence. So the same divergence of a vector in Cartesian coordinate system that we are going to discuss in the next class, how we are going to differentiate or represent this divergence in case of Cartesian system. That is nothing but if any volume, if you consider a parallelepiped volume or a spherical volume, it depends on three-dimensional structures. So in this unit, we are going to discuss only about the Cartesian, not about spherical polar coordinate system. Okay, so we'll see that part in the next class. Thank you.